closely at this precise movement. A mechanical claw snaps shut, secures its payload, and lifts it directly out of the frame. We are going to build exactly that, a fully functional, stationary pick-and-place robotic arm, driven entirely by the Quarky microcontroller board. This image displays the hardware layout we need to make it happen. You will use your Quarky board, an expansion board to handle the motors, 4 servo motors, a gripper claw, a 7.4-volt battery pack, and a set of acrylic arm pieces for the physical structure. By assembling and programming these exact components on your tabletop, you will learn the exact mechanical and software principles used to run large-scale factory floors and global shipping warehouses. Step 1 is structural stability. You must firmly mount the lowest section of your acrylic arm directly to a stationary base plate. From that secure foundation, we build upwards to create 4 distinct pivot points. These are the base rotation, the shoulder, the elbow, and finally, the gripper claw at the end of the arm. Make sure to fully tighten the brackets at every single joint. If the mechanical connections are loose, the weight of the arm will cause the motors to physically jitter and shake during operation. This diagram shows standard servo wiring. The cable splits, red routes to 5-volt power, brown to ground, and yellow to a signal pin. Connect your 4 servos. Map the base motor to port D1, shoulder to D2, elbow to D3, and gripper to D4. You must ensure that every electronic component shares a common ground connection. A common ground means all the negative terminals are linked together, providing a single reference point for voltage so the motors don't misinterpret the data signals. When you combine a tightly screwed acrylic structure with a unified, properly grounded circuit, you create a physical machine that behaves predictably. Next, plug your external 7.4-volt battery pack directly into the power input on the expansion board. We do this because running 4 active mechanical servos requires a massive draw of electrical current. The Quarky microcontroller, which acts as the logic center of our robot, is designed for low-power processing, not heavy lifting. Look at this schematic. It illustrates what happens if you pull all that motor power directly through the Quarky's 5-volt pin. The board will overload and fail. To avoid this, we use a power segregation architecture. The Quarky logic board receives its own steady, regulated 5-volt power via USB, while the power-hungry physical motors draw their energy strictly from the 7.4-volt battery attached to the expansion board. By isolating these 2 electrical systems, you protect your delicate microprocessors from the sudden voltage spikes that occur every time a physical motor starts moving. Now we move to the software. Open PictoBlocks, which is a block-based and Python coding environment. Select the Quarky hardware profile from the board menu and activate the servo extension to load our motor control commands. We need to break the robot's complete physical task down into 4 programmable states: the pick state, the grab state, the lift state, and the place state. This split screen shows our code. To initiate pick, we assign angles: base to 40 degrees, shoulder to 90, elbow to 120, and gripper to 0. Before closing, a 1-second time.sleep command forces a pause, stopping arm momentum before the gripper clamps down at 90 degrees. Once the object is secured, you write the next set of angle instructions to raise the shoulder and elbow for the lift state, and then rotate the base motor to execute the final place state. Writing automated movement is simply the process of translating physical 3D space into sequential lists of mathematical coordinates. Before you run your full program loop, halt the sequence and manually test each individual servo angle one by one. In the real world, gravity, friction, and the weight of your arm will affect your trajectory. You must manually adjust the angle numbers in your code slightly until the arm aligns perfectly with the physical target object on your desk. If your gripper is dropping its payload, simply go back to the code for Servo 4 and increase the maximum closure angle so it bites down harder. Even with perfect calibration, this base model has a limitation. It executes its sequence blindly. It will close its claw and move to the target location, whether an object is actually there or not. To fix this, you can mount an IR sensor, which uses infrared light to detect nearby objects, or an ultrasonic sensor. This allows the arm to verify an object is physically present on the desk before it ever triggers the first line of the movement code. Manual calibration and environmental sensors are the tools you use to force digital instructions to cooperate with real-world physics. With the code calibrated and the loop running, your finished robot will continuously pick, lift, and place its target without any further human input. Looking at this photograph of a commercial packaging facility, you can see the exact same sequential logic at work. This heavy-duty arm uses calculated coordinates to lift boxes directly off a moving conveyor belt. And in this image of a vehicle manufacturing plant, massive industrial robots rely on the same power segregation and precise servo angles to safely manipulate an entire car frame. You have successfully engineered the foundational logic that powers modern automated industry. Your next challenge is to integrate a color sensor and rewrite your loops to create a machine that actively sorts objects by visual properties.